Looks like we're live. Like everybody. I have 20 people, including people here. I was like, Belinda's going to be too lazy to show up. Looks like we're live. Like everybody. I have 20 people. 30 people here. I was like, Belinda's going to be. Hey, Chris. I told him to check and see if it was working. Definitely need to mute this. I would just turn on. I can't to stream, right? I was going to do that, but I can't. At least sign out. Well, I'm doing it through Hangouts. I know. Checkmate. No. It's muted now, but. Yeah, am I late? I see how it is. Pretty good. Yeah, pretty good name. Not pretty good. Yeah. Do I need to step out for a second? That was good. The audio, I would have preferred it. Yeah. Enunciate. I don't know how the camera is, but it's mine. Yeah, that's true. Oh, that's perfect. We can merge the missing frames. Reconstruct the whole thing. Are we going to keep this lighting? Sometimes they like to turn off all of the lights. All of the lights? Hopefully it's not too dark. Hey, wait, turn off the lights. Let's check the stream. That's pretty dark. Yeah, if only my webcam could do that. That's pretty dark. I'm just a silhouette there. Hopefully we let a little more light in. Let's at least leave the curtains open. Yeah, that actually helps quite a bit, at least for the laptop. This light will keep everyone awake. Yeah, I like that. I would prefer that on. But then you can see what everyone's. Whatever. Not that they would. Oh, see everyone's sleeping? I prefer that. The best part about people watching online is they can fall asleep. No. Yep. Chris is like. I should eat a snack. Didn't eat any breakfast. Somebody give me a timer. You go to one of those. Yeah. Oh, shoot. Should make sure the clicker works. That would be bad. Oh, you're on the wrong side. You try it over here. Pretty interesting. Right, if you wanted to come up here, there's room there. I think down there is good disengage. Last time I tried to do another friend, you flying, like your audio would be better down there? Yeah, here's the line. Right. What's the quality of it? 1080. 1080. Good reminder, like, yes, I do. Oh, yeah. You see, the battery should last an hour, right? Full? Yeah, probably. I don't know. I've never tried to say an hour. I think Brian's last. Yeah, this one. All right. Breakfast champions. And it's highly cold. On this one. Yeah, that's exactly what you want. Check that on the arms of the left. Yeah. Oh, heart rate. Yeah. Yeah. Do it right now. Very good. I'll try. PhD. Can this be put into it? I don't think so. 107. Okay. And then. Please, it's lower than British. Yeah. 60. Too much of English there I am. I don't understand that. You're right. Yeah. You compare here this one. Look, yeah, I didn't practice it. I went through it once this morning, and I was like, what am I? I don't like it. Yeah, I don't like that. Yeah. I did not want them on. Well, you know, the hungry. They could like speed it up. Or yeah. Perfect. Yeah. So we did a 7-minute stretch. But if you fall asleep, Howard, what? Oh, I didn't expect you to. Howard. What? You got it right, Howard. Not Howard. I don't want I had it. Yep, right there. But what was it? Yeah. We're not being here 2 more years, but I need to. So I graduated 2 years ago. They don't know. Everybody's sleeping. Whoa. You're more well rested. I mean, how they can that's one year. Oh, wow. Wow, they're not in the same lab. Well, I'm saying. Is there something? Yeah, I saw that. Oh, really?
That would be kind of, I have to.
I feel like you actually might be able, depending on, it's the weakening mechanism, like might be able to, I want to prove it, like, unless they neglect that happens for a weakening mechanism. Maybe it's not physically possible, but like, my idea is like that would require more of that radiator to actually activate that weakening process, right? To make that kind of sharp impulse to actually be able to happen. Is that something parallel to that?
I think Did you get my comments yesterday?
Yes.
Guys, we're going to start. All right. Thank you everybody for coming. So today we have Steven's defense. Yay. So Steven came to us with a bachelor's in engineering physics from Cornell and spent several fun years studying earthquakes, modeling them, finding some pretty interesting conclusions about energy balance and stress drops and things like that. In the meanwhile, he was also active in the Seismolab or GPS soccer team, as well as participated in the actually participated in Caltech Graduate Student Council on the Social Events Committee. So hopefully these were fun and productive years. And after this, Steven will continue to research, but some perhaps slightly different things as the research analyst for Operations Evaluation Group in Center for Naval Analysis, somewhere close to Washington, D.C. Okay, so hopefully use his problem-solving skills to help Navy do very well. Certainly an important task. And today he will tell us about his research into stress change and energy budget of earthquakes through physics-based modeling.
Thank you, Nadia. So like Nadia said, I'm going to talk about stress change and energy budget of earthquakes using physics-based modeling. I'll start off with a picture of the San Andreas Fault from the air here. This is kind of the main thing in California we think about when we think about earthquakes, and that's what we're going to be investigating. Let me just start off with why studying earthquake physics is important. Everyone likes to show pictures like these when they give an earthquake talk. This is from the Central Mexico earthquake from this year, September 2017 in Mexico City. And you can see even in today's modern age, when it feels like we have technology that solves so many problems, we're still kind of unable to solve the earthquake problem. And it's a difficult one, but studying earthquake physics is important to be able to better be able to predict events like this, and at the very least, do better risk assessment for high-risk areas like Mexico City, like Los Angeles, like Japan. And so that's sort of the motivation for our studies here, and that's what got me interested in earthquakes, was just seeing this fantastic and sort of a terrifying way phenomena be able to wreak havoc and wonder what's the underlying physics of that sort of process. So this is an outline of my thesis, and I'm not going to have time today to get into everything. Let me just take you through quickly. I'm going to start talking about our fault models and show you some simulated events. Primarily, my research was using a two-dimensional fully dynamic earthquake sequence simulation code. We'll talk about modeling a seismogenic region, creating these average curves that illustrate events, and calculating average stress drop and breakdown energy amongst some other energy quantities. I have results for models with just rate and state friction. That's in the printed thesis. I won't have time to go into it here, but if you're interested, you come talk to me or look at the printed thesis. I'm going to skip ahead in the talk to the somewhat more interesting results reconciling dynamic weakening with magnitude invariant stress drops, as well as increasing breakdown energy with event size. And I'll show you results for models with thermal pressurization. One really interesting result is this varying the velocity strengthening properties and its effect on stress drop. And unfortunately, I don't have enough time in an hour to get into that. So look in the printed thesis for that if you're interested. After which, I'll move on to a more general view of earthquake energy budget and looking at our efforts to capture different rupture behavior and see how that affects seismic estimates of different energies. In thesis, I've talked about seismically estimated breakdown energy, as well as this breakdown energy derived from dynamic and final levels of stress. Those won't be in the talk today. I'm instead going to focus on seismically estimated available energy and actual available energy, and radiation ratio and actual radiation ratio that come from those quantities. So it's kind of an outline here, and then I'll go to my conclusions. So let me just outline the methodology that we use in our group. We take laboratory-derived fault constitutive behaviors from other groups doing laboratory experiments on rocks, hoping to simulate the physics that we see on natural faults. Those are usually at smaller scale, always at smaller scale than earthquakes we see in nature. And from those, we can derive shear resistance laws relating shear stress on the fault through a friction coefficient to normal stress and potentially pore pressure if there's fluids on the fault. And we can see a couple of the equations here, rate and state friction, governing friction on the fault. These are the equations for thermal pressurization that I'll talk about a little bit later, where pore fluids inside the fault pressurize and relieve some of the normal stress through this term. From these shear resistance laws, we can make simplified models using computer code. We load them with slow tectonic-like loading, hoping to simulate what you might see in nature. So this is kind of a cartoon picture showing what we're looking at. We've got a velocity strengthening region where there's creep, a velocity weakening region where there's locked and potentially seismogenic zone, and then loading at one of the edges, just like you might see on the natural fault. And so with these, we kind of put it in a computer code. We ship it off to the supercomputer here, FRAM, down in the basement, let it run for days or weeks, and the results of that come back, at least from our code, with spontaneous fault motion over years. We're able to resolve all aspects of the earthquake cycle. So we can see pre-earthquake event, we can see co-seismic slip, post-seismic slip, and the time step, inter-seismic slip between events. With varying time step, we're able to resolve all those things. And the results look somewhat like this. I'll go through in more detail what this means. And then analyzing those results, we can use to improve our shear resistance laws or reject things that don't seem to work well when scaled up to sort of large scale models. And we can also improve on our simplified models, make them more complex, add in extra features from laboratory experiments. And it's basically an iterative process that allows us to improve on our understanding of earthquake physics through this modeling. So for today, I'm going to focus on using a 1D fault in a 2D medium. So here's our cartoon picture of the fault again. You can see it's a plane fault like you'd expect to see in the Earth. And because it's very computationally expensive to simulate the plane, we're going to collapse it down to just a line here, the red line. So think of all the properties on the fault here kind of being averaged down to this line. And so instead of having a plane, we have a 1D line fault, which extends infinitely repeating in this dimension. And we're going to load that just like a natural fault would be loaded. And we're going to have locked and creeping segments on it to produce earthquakes in a one-dimensional line fault. So this is just going to show you a sample seismic event here. You're going to see these kinds of plots a lot. So let's go through this. We've got the spatial distribution along the fault here in kilometers. You can see here we're showing a 5 kilometer or 6 kilometer segment of the fault. And then along the y-axis, we see accumulated slip. So think of this as points along the fault. And as the earthquake starts, the points will begin to slip upward. You can see the first sort of snapshot here of the rupture beginning. We overlay the properties of the fault on this. We have the locked region here, which is through the rate and state velocity weakening region, normally locked. We force the fault at the edges at plate rate, 10 to the minus 9 meters per second. That penetrates creep through this creeping region and allows it to load the locked region, increasing the stress, and eventually you nucleate an earthquake. See, this particular earthquake nucleated near the edge of the locked region, and we'll see it propagate outward as we go through time. So here's the second snapshot. You can see that the rupture started here in the nucleation zone, propagating to the right and left, and points are now slipping further, and more points are slipping. If we go through time a little bit more, you can see that the rupture is now propagated to the edge of the creeping zone here, which acts as a barrier. Doesn't want seismic slip, so it basically stops the rupture. But on this side, we're penetrating through the locked region, and so you can see the rupture is getting longer, and also the points are slipping more. Points in the middle of the rupture here have now slipped about 0.4 meters. And if we go forward through time more, we can see the rupture continues to propagate to the right, and points continue to slip. And then as the event arrests, we kind of get a distribution of slip on the fault. So going back to the spatial scale of the fault, you can see here that this earthquake ruptured from -6 kilometers over to about -1.2 on our fault. And you can see that we see a spatially varying distribution of slip along the fault. Points in the middle here slip nearly a meter, and points at the edges slip almost nothing. And so talking about the slip for this event is sort of a complex problem, because there is not one slip value for this event. There's a distribution, and it varies along the fault. This is a portion of an earthquake sequence. So that event I just showed you is part of an earthquake sequence that comes out of our code, any earthquakes. You can see here, I'm just showing you a portion starting at, we've accumulated 34 meters of slip on the fault already, and we can see many different types of events here. The event from the previous slide shown in blue. We produce large model spanning events here with several meters of slip. We produce small events on the edges, sort of medium-sized events. And so in one simulation, we're able to produce a suite of a range of event sizes and be able to study the characteristics of multiple size events, and also the trends as event size increases. So it's not just slip that varies spatially along the fault, but many other properties, almost everything. And so here is the accumulated slip profile I just showed you. And I'm now going to show you what stress evolution on the fault looks like. And so here we've got initial stress plotted in the solid line, and final stress plotted in the dotted line along the fault. And we can see a few different things here. One is that in the nucleation zone, we see this kind of peak of stress, allowing the rupture to begin there, the highest level on the fault, so that's not surprising. As the rupture propagates outward, we can see that it encounters lower levels of pre-stress, and then it encounters this sort of high level of pre-stress over here from previous events, which allows it to kind of continue past this point. And then it moves further to the right and encounters, again, low levels of pre-stress over here, which the rupture is unable to propagate all the way through, and so it arrests right around -1.2. And so we see spatially non-uniform initial stress, and also final stress is relatively constant along the ruptured area. You can see the stress increase here right at the edge, as well as on this end. But the stress drop or stress change along the fault, the difference between the initial and final stress, also varies spatially along the fault. Near the nucleation zone, we can see that stress drop is relatively high next to that, low in the center of it. Over here, we have a fairly high stress drop, and then as we come over to where the event arrests, there's actually a negative stress drop in this region. So if we want to talk about stress change for this event, again, we have a complex situation where there is not one value that we can say along the fault. We need to think of some sort of average value to represent this event. Let's look at some local behavior of points along the fault. And we can see that the local behavior varies too. It's not just the initial and final stress, but actual stress evolution. So I've picked out 3 representative points here, shown in blue, red, and green. And we have the blue point in the nucleation zone, the red point in the middle of the rupture, kind of where the rupture is moving along most happily, and then the green point here, which is closer to the arrest phase. We can see a few different types of behaviors here. I've marked the initial stress and final stress at each point with circles. The way our code works is the event is considered seismic when any point along the fault reaches 0.1 meter per second. So that's when this stress will be marked. And we can see that in the nucleation point, there's actually this aseismic evolution of stress before the earthquake starts. This could be in seconds, minutes, days. leading up to the event, and actually there's a decent amount of stress evolution just in the aseismic portion. And then after the event starts, we see, as we expect, the stress decrease. As the event slips, it releases stress on the fault and releases energy, and so we see a decrease in stress with slip, just like with these points. With our normal rate and state friction properties, we expect behavior sort of like this middle point, and that's what the majority of the points on the fault look like. So there's an initial value, the fault begins to rupture somewhere else. As the rupture front propagates toward this point, we see an increase up to the peak stress, and then a decrease down to its dynamic level. If we had just pure rate and state friction, we would see a constant dynamic level of stress here. But this event is utilizing enhanced dynamic weakening from thermal pressurization of pore fluids. That allows the stress to continue to drop with slip, and I'll get into exactly how that happens in a few slides. But just the important part here is seeing the different evolution. And then we see a slight adjustment of stress at the end of the event called stress overshoot, where the stress is initially higher and needs to adjust down for its static final value. The arrest point, again, we see less slip, but a similar evolution to the point in the middle of the rupture. And the same type of thing up to the peak level, down to a dynamic level that evolves, and then an adjustment to a final level of stress. So again, we need to think about how can we describe this event with kind of one illustrative curve or values that represent just the event rather than this spatially varying behavior along the fault. And we've developed methods, also using methods developed by others, for computing average quantities consistent with observations. So the evolution I showed you on the last slide, those stress versus slip evolutions at points can be averaged. And I'm not going to go into details about how that's done, but it's basically the points are scaled so that they all have the same slip, which corresponds to average slip on the fault. And then the area under the curve is conserved, so it's either stretched vertically up or down, and then interpolated and averaged, and it allows us to produce a single kind of illustrative average curve here for the event. So this is what this curve is, it's an average curve. And from this curve, we can derive some average values. For example, average stress drop. We have the initial stress on average on the fault, so by tau I bar here. We see the same evolution for the average curve that we did for the majority of points, where stress increases to a peak level, drops down to a dynamic level, in this case continues to weaken with the dynamic weakening. It reaches some minimum level here shown by the triangle, and then it might re-strengthen slightly, and in this case, because this event is crack-like, where all points along the rupture are all moving at once, I'll talk about the difference between crack-like and pulse-like in just a sec. With crack-like events, we expect a stress overshoot, usually pretty small, but that's what this adjustment at the end is. So the average stress drop for this event calculated is just this initial average stress minus the average final stress. That's average static stress drop. We can also look at some energy quantities from this average curve. First, looking at the total strain energy released, or basically the total energy released in the event, released as breakdown energy to break down the fault, radiated energy as seismic waves, and frictionally dissipated energy, which I'll get into in just a sec. They're shown here. That strain energy release is given by this. It's shown as the dashed area here. And that extends all the way down to 0. I've cropped the plot at 20 just to provide clarity on the dynamics here. But the total strain energy release is just all the energy released during the earthquake. That can be subdivided into breakdown energy, or the energy used to propagate the rupture forward and break down the fault. And that's the area under this curve down to its minimum level. So it's the dotted region here. And that can be basically integrated over this curve from the initial value area under the curve down to this minimum value, all this area right here. If we want to calculate the radiated energy, we need to calculate one more quantity, which is this frictionally dissipated. And that's just the area below, actually it's shown wrong here, it should be below this triangle. The blue box should come up here. And that's energy dissipated through friction on the fault due to frictional sliding. If we take the total energy released, we subtract off the frictional energy, and we subtract off the breakdown energy, what we're left with is the radiated energy, radiated as seismic waves. That's shown in this shaded region here, and you'll notice there's a chunk missing here. That's due to this strength excess here as the event moves toward its peak stress. This chunk matches up with this area, and so because the radiated energy and breakdown energy must add up and fit inside the trapezoid, we have to remove a little bit here to get to the actual radiated energy. We can also calculate a radiation ratio, or radiation efficiency, and that's defined as the total amount of radiated energy over available energy for radiation and breakdown, this sum here. And I'll get into more details about that later, but it basically just shows a comparison of the size of the radiated energy to the breakdown energy and how important those are in the rupture process. So I just showed you a crack-like event. Here's an example of a pulse-like event. You can see, unlike the previous event, let's go back just for a second. So here, we'll get back to it later. You can see instead of all the points slipping at once, where we have those kind of increasingly large half circles, now we have what started off like a crack here has now turned into a pulse, sort of a broad pulse. And instead of all the points slipping here, there's only a sharp slip pulse of points slipping, whereas points here have arrested and points here are not yet slipping. And if we look at the average curve for an event like this, we can see the same type of behavior, increase the peak stress down to a dynamic level, but instead of an adjustment down at the end, we see this stress undershoot. Stress has undershot what it should be statically, it moves back up, and so this is qualitatively and quantitatively different, and that'll have an effect on our seismically estimated quantities. And we see in the previous event that the stress undershoot was small, but if we have a very sharp pulse, we can see that the stress undershoot can be significant. So here's a sharper pulse here, you can see very sharp. And in this case, the stress undershoot here is about 10 MPa, whereas our stress drop is only 2 to 3 MPa. So in this case, the stress undershoot is much larger compared to the stress drop. So when we talk about the idealized behavior of faults, usually we think of a picture like this, where the initial stress is equal to the peak stress. It drops down to some dynamic level of stress, which is equal to the final stress here. And in that case, calculating these energy quantities is relatively straightforward. You can see the total energy available for radiation and breakdown in this triangle, and it neatly divides into breakdown energy here, radiated energy here. But as I've shown you for the previous two events from our simulations, for both crack-like and pulse-like events, there's significant differences from this idealized model. We see that the initial stress is not equal to the peak stress in both cases, this strength excess going up. And we see that the dynamic level is not constant, drops down to a varying level of dynamic stress, mostly due to our enhanced dynamic weakening. And we see that the final level of stress is not equal to the dynamic level. We have a stress overshoot here and a stress undershoot here. And so we'll see how that affects our calculations of energy quantities seismically. Now that we've gone through that introduction, let me show you the observations for these quantities, starting with stress drops. So this is a plot from Abercrombie and Rice paper from 2005. They're showing different size events. So source dimension here increasing and seismic movement. Both of those increase as events get larger. So larger events are up to the right. And we can see they have plotted lines of constant stress drop here on these events. And so even though the event size is moving from 10 to the 9th, 10 to the 21st, 12 orders of magnitude in event size, the stress drops actually fall relatively, not constant, but we're going to call it magnitude invariant, because for small and large events, the stress drops fall between 0.1 and 100, and actually the majority between 1 and 10. So as events get larger, the stress drop doesn't change. It's basically magnitude invariant. Secondly, we see that breakdown energy, that dotted area under the curve, is observed to increase with event size. This plot is from Jim Rice's paper in 2006, and we can see events increase in slip corresponds to an increase in event size. And so as events get larger, breakdown energy also increases. Third, we see that radiation ratios inferred for seismic events are usually less than 1. This is from Ventakaraman and Kanamori 2006. And you can see that there are a few outliers here. These are for much large events. We can see that most of them fall between 0 and 1, but there are a few outliers with values greater than 1. That's what we call this radiation ratio, although
called radiation efficiency. And so we're going to say that inferred radiation ratios are usually less than 1, not 100% of the time. We also see from the lab, as another observation, that weakening may occur at high slip rates. So this plot is showing the results of many different laboratory studies on friction. And we have friction coefficient here against slip velocity in the lab. And we can see that for plate rate, very slow rates, we get friction coefficients between 0.6 and 0.8 as we expect. But as we increase the velocity, and actually right as we approach seismic velocity here, the friction coefficient weakens dramatically, almost to nearly 0. And so from that, we can infer that there must be dramatic weakening occurring on faults at high slip rates. Here. One mechanism for this dramatic weakening is thermal pressurization of pore fluids. That's what I'm going to use for the majority of this talk. And so as the fault slips, it heats up just like when you slide your hands together and you generate heat. It generates frictional heat on the fault. If there's fluid trapped within the fault, the frictional heat increases the temperature on the fault, increases the temperature of the fluid, and through this coupled differential equation, we can see that it increases the pore pressure of the fluid. We've got our shear heating term here. As long as the half-width of the fault is not too large, which would dissipate the heat over a larger area, as long as the thermal diffusivity is not too large, as long as the heat's not leaking out too fast, and as long as the hydraulic diffusivity is not too large, the fluid is not leaking out too quickly, then we'll see an increase in temperature coupled with an increase in pore pressure. And if we go back to our shear resistance law, we can see that effective normal stress here is defined as normal stress minus pore pressure, and that allows effective normal stress to drop as the pore pressure increases. As this drops, so does the shear resistance, and so we have dynamic weakening due to thermal pressurization of pore fluids. Again, this depends on the rock permeability, so this effect can be rather dramatic or can be kind of not involved at all, depending on the properties. So moving into the second part of the talk, we want to see, now that we've gone through the observations, can dynamic weakening explain all of the observed trends simultaneously? As we just saw, we see stress drops of magnitude and varying. We see breakdown energy increases with event size. We see that radiation ratios are often less than 1. And we see that dynamic weakening likely occurs during seismic slip from laboratory studies. So the question asks, can dynamic weakening be reconciled with these observations? We're going to use our physics-based modeling approach to study the implications of this. Before we get into the results, let me just discuss why this isn't inherently obvious, and it is possible for dynamic weakening to have magnitude and variant stress drops. So we'll present what may be an intuitive view for some people, which is that for small events and large events, we expect the events to nucleate at similar levels of pre-stress. After all, when the event nucleates, that's related to the strength on the fault, and so they should nucleate at similar levels. We know that small events don't slip as much, so they won't weaken as far, decrease in stress as far, whereas large events will slip more because they're larger and weaken more, and thus we would expect smaller stress drops for small events and larger stress drops for large events with this dynamic weakening present. And that's not what we see in observations. So what could be going on here? Well, we present a possibility, which is that average initial stress is actually lower for larger events. And this is possible because while the nucleation zone may be at similar levels of pre-stress, small events rupture relatively small areas around the nucleation zone. So when we talk about the average initial stress, we're averaging a small area that probably has pre-stress similar to the nucleation zone. So the average initial stress will be similar. Whereas a large event will rupture a much larger area, and it will be able to incorporate areas that are lower pre-stress that weren't ready to rupture into its ruptured area. They rupture anyway because the event is so large it propagates right through them. So if we average the initial stress over the entire ruptured area, we get a lower initial value. We'll see the same sort of evolution, increase to peak, and decrease with slip due to the dynamic weakening. And for the larger event, it will weaken to a lower level. But because it started off at a lower initial level, stress drop between the two may actually be roughly constant. So spoiler alert, in our simulations, we do see that larger events have larger breakdown energy, but similar stress drops. So here are 3 events, small, medium, and large, from one simulation. You can see in the accumulated slip profile how much bigger it gets as we go. We can look at the average curves here, and we see as the events get larger, as we expect, the average slip increases, the dynamic weakening continues, and so the area underneath the curve, shown in this dotted region again, increases as events get larger. Fantastic. We also see, as we expected, that the initial stress decreases as events get larger, and the final stress decreases as events get larger, but the offset, the stress drop between the 2 points, is actually roughly the same between them. And in fact, for these 3 events, it's almost identical, 7.1 megapascals, 7.1, and 6.8. So again, breakdown energy increases, but stress drops stay magnitude invariant. Let's look at more than just 3 events. Let's look at all the events from these simulations. Here I'm plotting 3 different simulations with different properties on the fault. One with 50 megapascal normal stress, one with double that, 100 megapascal normal stress, and one where I've increased the efficiency of the thermal pressurization by decreasing the hydraulic diffusivity 10 times. So that lets the fluid leak out more slowly and allows the thermal pressurization to be more efficient. And we can see, as we'd expect, the initial stress shown by these open circles decreases kind of smoothly as events get larger for all 3 cases. The final stress shown in the diamonds also decreases smoothly as events get larger, but the offset, the difference between these, which gives the stress drop, is actually pretty much constant for a given simulation here. Stress drops are shown at the top. We can see over 2 orders of magnitude of slip, we have basically magnitude invariant stress drops in all 3 cases. Changing the properties changes the absolute level of the stress drops, but doesn't change the trend. One thing I'd like to point out real quick here is our model spanning events are plotted in filled in circles here. And you can see those don't follow the trend. This goes back to the velocity strengthening properties of the fault at the edge. And again, I don't have time to go into it now, but just quickly say, if we change the velocity strengthening properties, we can get either an increasing trend, a neutral trend, or a decreasing trend for these model spanning events, depending on how far they propagate into the barrier region of the edge. So I'm not going to go into that now, but if you're interested, then check out my thesis. We look at breakdown energies. As we expect, we see breakdown energies increase with event size. So here, over 2.5 orders of magnitude of slip, we see breakdown energies increase. Let's go back to the observation that I showed earlier here from Rice 2006 and overlay our data on top. Let's see how well we're reproducing that. We can see it actually matches up quite well. We're only able to get the sort of high end of the scale here due to computational limitations, but our events in all 3 cases actually match up very well with the observed quantities. Lastly, we'd like to look at radiation ratios. These are the seismically estimated ones. I'll go into detail on that in just a sec, but suffice it to say that for models with thermal pressurization here, all of the radiation ratios are less than 1, which is good. That matches up with what we see for most observed events. So now that we've seen that thermal pressurization can do a pretty good job of reproducing observed quantities for events, how does rupture behavior and its difference between crack and pulse-like or behavior in between affect seismic estimates of quantities? We know that many people think large events may be preferentially pulse-like. Tom Newton said in his 1990 paper, and Vieska and Garagash in their 2015 paper when calculating breakdown energies, assume large events to be pulse-like. So do these different behaviors, crack to pulse-like, affect seismic estimations of earthquake energy quantities? Let's go back to our idealized view here. In the top left, you've seen this before, and I've also got an idealized view with an undershoot, indicative of kind of an idealized pulse event, and idealized with overshoot, kind of indicative of an idealized crack event. Again, we see that the total strain energy released, as before, is the sum of the breakdown energy, radiated energy, and frictionally dissipated energy. That's the entire area underneath this dashed line. We can calculate the actual available energy. By definition, is the sum of the breakdown energy and the radiated energy. So we call that delta W naught A, or actual available energy. We can see in the idealized case that this actual available energy actually corresponds pretty well to something that we can seismically estimate. It's very difficult to estimate initial and final stress quantities, absolute values of those on the fault, or dynamic levels of stress on the fault. But it is fairly easy to observe stress changes, so the stress drop. In this idealized case, we can see that for the available energy here, into breakdown and radiated, we don't actually need to know the initial and final levels. We just need to know the difference here. And so the seismically estimated available energy here is hatched like this, and we can see that it's just this triangle, 1/2 times the stress drop times the average slip of the event. And in the idealized case, that equates to the actual available energy. However, if we have an idealized pulse or crack, or just a normal crack pulse that's more complex than this, we'll see that this isn't necessarily the case. For cases B and C here, we can see that we have a stress undershoot. Here I'm denoting it as gamma delta tau, so some multiplier times the stress drop, and again, undershoot here, overshoot here, which is usually pretty small, but can be non-negligible. And in this case, the actual available energy, the sum of the breakdown and radiated, this dotted region and this shaded region, is different than our seismic estimate. Different by this factor should be times delta part here. And so we can see for the pulse-like event, the hatched region for the seismic estimation is actually smaller than the true value. And that's for gamma greater than 0. And for the crack-like, we see that the seismic estimation is actually larger than the true value. So we'll look at some specific events, but there's a difference here. And depending on the size of this undershoot or overshoot, we may have drastically incorrect values when we seismically estimate them. We can take radiation ratio from these as well by taking the radiated energy over the actual available energy. That will give us the actual radiation ratio. And we can compare that to what we estimate seismically, which is the radiated energy over this seismically estimated available energy. And we'll see how those match up for some events and differ for other events. So we're going to explore crack-like, crack-to-pulse-like, and pulse-like behavior. And we're going to do this through 4 different models. We've got standard rate and state model. I'm not going to discuss the results of that too much. We've got rate and state with thermal pressurization, like I showed earlier. And then we add in a second dynamic weakening type, flash heating, which is basically due to sort of flash heating of microcontacts on the fault and almost like micro melting that allows the fault to weaken rapidly at the beginning of slip and then kind of remain at a lower level of dynamic stress. And that leads to more pulse-like behavior. So if we add that in, we expect to see more pulse-like behavior here. And if we just use more pronounced flash heating, then we'll end up with much more pronounced and sharp pulses. So we should get a suite of varying behaviors depending on these models. So here is the same crack-like event that I showed you earlier using thermal pressurization. Here we see a slight overshoot at the end, and we can see that the seismically estimated available energy, delta W naught, slightly overestimates our actual available energy. So this hatched region here is actually a little bit larger than the radiated and breakdown energy by 20%. So our ratio here is 0.8. We can see that our gamma here is relatively small, -1/8 compared to the stress drop. So it's not negligible, but it's a small change. And even though these are off by 20%, we can see that they actually match pretty well. If we look at the radiation ratios in both cases, the actual is 0.47 and the seismically estimated is 0.38. They're not exactly the same, but they're close, and they're both between 0 and 1. So for crack-like events, we see that doing this seismic estimation makes sense and is actually pretty accurate. For events that transition from crack to pulse, this is again the event I showed earlier, you can see it's crack-like initially, transitions to a broad pulse. Here we have a stress undershoot, and gamma is relatively small, about 1/2 in this case, half the stress drop. And we can see that the hatched region here, so the seismically estimated available energy, is smaller. You can just see it by eye than the breakdown energy here and the radiated energy here combined. The ratio of the two is 2.13. So we're sort of moving away from those being matching estimates. We can see that the actual radiation ratio here is 0.42, whereas the seismic estimated is much larger, about 2.3 times. And so it's close to 1, still less than 1, but 0.89. If we look at a stronger, sharper pulse-like event, we can see that this event has more significant undershoot, and the available energy here is underestimated nearly 10 times when we do it seismically. So Here, again, the large stress undershoot. Gamma in this case is 4. And so the ratio of the actual available energy to the seismic estimate is 9. It's almost an order of magnitude different. And that leads to radiation ratios. The actual, again, is between 0 and 1. But the seismically estimated is 5.57. So for a very sharp pulse, we see that this strong, this large stress undershoot actually has a large effect on both the available energy estimated seismically, and then because of that on the radiation ratio. And if we calculated seismically estimated breakdown energy, we can also see that that has a large effect. But I'm not going to go into that. Let's look at all the events for these simulations, and we'll see different trends for different types of behavior produced by these models. So this is the second model, rate and state friction with thermal pressurization. And we can see that in this case, like we expect, most events are crack-like, and so they would plot down here. A few events transition to pulse-like behavior, so they plot above. So in crack-like events, we see that the seismic estimation slightly overestimates, so the ratio is less than 1. And for the transition events, we see that the ratio is a little bit larger than 1, but the majority of these events are crack-like. If we add in flash heating, we see there are still some crack-like events, less than 1 for the ratio. But as events become more pulse-like here, especially for larger events, we see that the ratio increases. So these events are, again, more pulse-like, and the seismic estimation is underestimating the actual available energy for these pulse-like events. If we look at the just rate and state friction and more pronounced flash heating, we can see in this case all of these events are pulse-like. None of them fall below the line, and we're actually looking at ratios 5 to 10, somewhere more than an order of magnitude different between the seismic estimation, drastically underestimating the actual available energy. If we look at radiation ratios for all 4 models, we see that both the standard rate and state model, again, I didn't really talk about that too much, but I'm showing it here just for your information, and the rate and state plus thermal pressurization both produce mostly crack-like events, and we can see that the radiation ratios, both seismically estimated and actual, plot between 0 and 1, and actually match pretty well for these events. Once we add in flash heating, which allows events to be more pulse-like, we can see that things diverge a bit. Here we see, at least for the smaller events, potentially more crack-like, and the radiation ratios agree fairly well, but as events get larger and more pulse-like, we see that the seismic estimation for radiation ratio increases above 1, whereas the actual radiation ratio remains below 1. And then the biggest difference is shown in this more pronounced flash heating model, where we see, again, completely pulse-like events, and all of the seismic estimations of this radiation ratio are greater than 1, whereas the actual radiation ratio is actually still less than 1, as you would expect. So, in conclusion, we've implemented methodology for averaging this complex, spatially and temporally varying behavior of simulated dynamic events, which allows us to enable comparison with observations. We see that our fault models with rate and state friction and with additionally dynamic weakening due to thermal pressurization of pore fluids reproduce several key observations. We were able to reproduce magnitude invariant stress drops, increase in breakdown energy for large events, and we also see radiation efficiencies between 0.5 and 1. However, they produce mostly crack-like behavior or behavior that's transitioning between crack-like and pulse-like. Seismically estimated values for available energy and breakdown energy and radiation efficiency are derived from that. Those depend on the rupture behavior. So for crack-like events, as we've seen, the seismically estimated available energy and seismically estimated radiation ratio actually match pretty well with the actual ones. But for pulse-like events, we see that this actual available energy can be much larger than the seismic estimation. And so if large events are indeed pulse-like, then the energy budget is different than what we currently imagine in an idealized case. And due to larger available energy than currently estimated, we see that breakdown energy would be very complex to calculate. We would need to know the magnitude of the stress undershoot. That's very difficult or impossible to measure. And if the stress undershoot is quite significant, seismic estimations of both available energy and breakdown energy derived from that would be potentially very inaccurate. Before I finish, I just want to make a few acknowledgements here. I would like to thank the support staff first, Rosemary, Priscilla, Donna, Kim, and Carolina, for making things very smooth for me during the 6 years here, going on trips, going to conferences, the Seismo Lab retreat, all the stuff that they did setting up this morning. Really thankful for that. I'd like to thank my committee here, Jean-Wen, Jean-Philippe, Victor, for helping me through the PhD process. I really have to thank my thesis advisor, Nadia, for pushing me. There were definitely some difficult times during my 6 years, and she kept me going and really pushed me to the finish line when things got tough. So thank you so much for that. I got to thank my office mates, Benjamin, he's out at sea right now, but he's here in spirit, and Stacy, and of course the coffee machine that they bought, which was vital to the last week of writing my thesis. So thank you guys for that. I got to thank the research group here with Nadia. You guys were super good helping debug the code. Any sort of computer problems, conceptual problems I had. Thank you, Natalie, Marcello. June was not here, but he was super helpful. Vito, Sameka also graduated, but we went through a lot of it together, and this was us in Corsica. So I guess sometimes conferences do end up in nice places. But thank you guys so much for helping understand the results and debug the code. A lot of that is very time consuming, and I couldn't have done it without you. I'd like to thank my classmates that I came in with, sort of the last man standing here. Chris, Brian, and Sameka already graduated. Asaf, who's not pictured, the all-star that he was. They were all very helpful. You guys got me through first year with the classes, working on problem sets together. You guys kept things lighthearted and fun. Everyone was really supportive in the last week when I was finishing things up. I thank you so much for that, for not forgetting me and being around and available. I'd like to thank my roommates, Howard and Vipul, who I lived with for a couple of years, for keeping things lighthearted outside of work, keeping things fun and keeping me happy. Grad school is a long slog, and you guys, it would have been tough to make it through. I'd like to thank my family. My mom and dad are here right now. They flew out last night. They're up top, you can see right there. And their flight was delayed like 4 hours, so they got in it after midnight, 3 hours of sleep. But thank you for being here and supporting me. And my brother and sister, Christine and Jameis, are both still on the East Coast. They couldn't be here, but thank you for your support too. And then I have a lot of friends to thank, and most importantly, I got to thank my girlfriend, Bailey. She's not here right now because we're moving to DC this weekend, and she already went. So she's setting up the house and getting things going, and I really appreciate that. And the last few weeks have been really hard, and I'm so thankful that she stood by me and was there to support me and did everything that she could to help me get through this. And it's going to be great on the other side out, and starting our new jobs and getting back to life without all of the stress of finishing a PhD. So thank you so much. Okay, that's all I have.
Thank you, Steven. Any questions? So we will have right now, the questions from the audience, and then we have to ask questions. What are you going to say later? Tom.
So you had a model with a strong rate we can make sharp slip pulses. Did they higher fracture energies for that? What it didn't have high fracture? I think the evidence showing the field is the find those high.
You're talking about cases like this, you mean?
Yeah.
So, yeah.
Remove all
Remove this part.
Yeah.
Yeah, so I think it's difficult to say our models produce this type of behavior. And so you can talk about, based on the stress undershoot, what the available energy is like, but it's difficult to talk about how that partition breaks down in radiated energy. And so obviously, given our assumptions and given this model, we're able to produce events that look like this. How that's partitioned in nature is an open question, and I think it's difficult because you don't really know how this stress distribution happens during the event. I mean, obviously, you can draw whatever kind of curve you want here. You could make breakdown energy very large and small radiated energy. You could make breakdown energy very small, as you're suggesting, and then you have a very large radiated energy. Just from this, we can say that our available energy is dramatically underestimated, but how that's partitioned into breakdown and radiated, we don't really know. So yeah, our models are producing this type of thing. We haven't been able to explore all the different types of models and all the potential different types of curves that come out of this. Hopefully, after I'm gone with the layer, might look into this a little bit more. Could one produce a model that has sharp pulses like this and very low breakdown energy and most of the available energy put into radiated energy? It's certainly possible. But just because you can draw the curve like that doesn't mean it's going to be able to come out of any sort of friction. Yeah, I haven't investigated that behavior robustly enough to make some conclusion. So we'll see.
Have a question? So earlier, in one of the earlier slides, you had observation, right? And then later using the modeling, radiation efficiency. So for the radiation efficiencies that were observed that were greater than 1, were those also larger than?
Yeah, this here is actually just showing large events, these magnitude 7 and 8. So you can see even for large events, there's actually a variety of behaviors just for observed quantities here. A lot of them are still less than 1, but some are greater than 1. And our models would suggest that if you end up with a radiation efficiency greater than 1, that's indicative of a pulse-like event. So a lot of people think that these events are pulse-like, and our results show that suggests that they likely are pulse-like.
Right.
Yeah, it's difficult to say, but at least crack-like events are able to reproduce radiation efficiency less than 1 consistently. So you would think, at least for smaller events where most of them are between 0 and 1, those are probably crack-like. For large events, maybe there's varying behavior, but it's hard to specifically say what's crack or pulse. But our results would suggest that if you have ratios larger than 1, it's more pulse-like. And you could see the ones that were transitioning weren't necessarily over 1, so you can have pulse-like behavior with some crack pulse transition in it, and you'd still end up with radiation efficiency here. Yeah, I mean, yeah. So the let's see, basically in these equations, the strain energy released is the total energy released during an earthquake that we think about. And so that's just by definition, what kind of things can the strain energy be released into? It can be released into breaking down the fault, radiated as seismic waves, and this frictionally dissipated the fault energy. So basically what we're trying to get at is how is this energy partitioned into these, and how does that affect the rupture dynamics? We have a highly radiating event that has a very high radiation and low breakdown. Do we have one that's not radiating very much and most of the energies need to break down, in which case G would be large and ER would be small? If we knew the absolute level of stress, we'd be able to calculate this frictional dissipation. That's difficult to get at. So yeah, I mean, looking at how the total energy release breaks down into these is sort of the important point here, but it's difficult for observed events because our simulations, we can draw these nice curves and we know all the parameters and we can output stress and slip rate at every point, every time step. But for real events, you have to infer a lot of these quantities, and it's difficult, especially to get at absolute values of stress. And so it makes it difficult to get at what these quantities are for real events.
Question? Okay, let's thank Steven again for a nice talk and being a good PhD student. So now we will move into the physical defense part. You're going to a different room, right?
Yeah, 212 is where we're going to be. I don't know where
So
the...
that's some good lunch. Cold lunch. Well, I think the both functions are there.